section 8.7, here's really what we've got, okay? And when it comes time to do that second portion of the test, whenever that happens, you'll have lots of triangles to work with, lots of triangles where you're supposed to find angle measures and side lengths. You'll have to be able to assess the situation and know what the tools are that you have to apply and how to apply them. I mean, if it's a right triangle, then it's just like straight trig. You don't have to drop in an altitude. But if it's not a right triangle, you will have to drop in an altitude, and then you'll have to do significant algebraic work to get to the answer. Sometimes more than others, but some algebraic work together with the trig. So, and you need to know which kind of case it is to know which kind of work to expect. Well, in section 8.7, the kinds of cases that we had were the angle side angle and the angle side type cases. And what that really means is this. It means that we knew the angles and the side, okay? Now, as you know, I've known for a long time, if you know two of the angles of a triangle, then the third is an easy computation. That's just the triangle angle sum theorem. So if we say angle side or angle side angle, that really means we know the angles. Maybe not all three of them immediately, but very quickly we can get them. So we know the angles and the side. And what we want to get is another side. That's the problem. When you know the angles inside of a triangle, how do you find another side length? That's what 8.7 is about, and that's what the law of sines will allow you to do. So let me derive for you the law of sines. And it's not particularly hard to do. I will do it for the case of an acute triangle. You know from our discussion of altitudes that not all altitudes lie inside the triangle. Sometimes altitudes go outside the triangle, and you need to know when they do because it determines the work that you do, the values that you have. Let us say in this case that the triangle is acute. I won't consider the other cases as well because it works out in a very similar fashion. But we do know in the case of the acute triangle that the altitudes are all on the inside of the triangle. Okay, so let's say that we have an acute triangle with an angle of measure alpha, another angle of measure beta, and let's say that opposite the angle alpha is the side length A, and opposite the angle beta is the side length B. Okay? Now, what I'm about to do is derive a formula that relates these four quantities together. And then once I'm done, I'll reflect upon that with you. It's really very important and powerful. All right, so my suggestion is this. And this is the same suggestion that I made a couple of days ago when I talked about how one does these problems, the angle side angle and angle side type problems. Drop in an altitude and do it such that the labeled sides become hypotenuses, okay? So A and B are now hypotenuses of right triangles. And almost always, and I'm sure you did this in the problems for 8.7, hopefully you've done some, you worked with the length of that altitude, which is almost always called h, okay? Per height, of course, that will be very important in the chapter on area, but for now, we'll just say h and not worry about why we would call it h. All right, we can now do trig, okay? We can now do trig. You see that we have two right triangles. You see that alpha and beta are acute angles, one of one of the other. So we can now write down trigonometric equations. We can write down, for instance, this, that the sine of alpha is, well, you tell me, what over what?
It is A over, wait, no.
What is sine by definition?
Opposite over hypotenuse.
Sine is opposite over hypotenuse.
So it's H over B.
That's exactly right, because it's the right triangle that's on the right-hand side. And the leg opposite the alpha is h, and the hypotenuse is b. So the sine of alpha is a over b. And then let's switch over to the other triangle, and now write sine of beta. So the sine of beta is what? That is exactly right. It's h over a. Now let's do a little bit of work with these. Have just a little bit of algebra to do. Let us solve both of them for h. That means that on the left equation, we would multiply both sides by b. On the right equation, we would multiply both sides by a. I'll show you the result. This is not difficult. So I will get h is b times the sine of alpha. And then for the second equation, I will get that h is a times the sine of beta. So we have two expressions, b sine alpha and a sine beta, that are both equal to h. And it is still true that quantities equal to the same quantity are equal to one another. So it is now, we may now say that b times the sine of alpha is a times the sine of beta. And this could be called form 1, LOS, is law of sines. Okay? This could be called form 1 of law of sines. It's not the form that's most commonly used, but it is a form of the law of sines. However, let me transform it into its most common form. And the way that it gets transformed into its most common form is we do a little division. So let's divide both sides by b times the sine of beta. I believe that's what I want to do. Yep, that's it. So I divide both sides by whatever I want. What I want is b times the sine of beta. So on the left-hand side, b over b becomes 1. On the right-hand side, sine beta over sine beta becomes 1. So what I get is this, is that a over b is equal to sine of alpha over the sine of beta, which is extraordinary. I'm glad that somebody did that, right? Because that makes me suspect that you have an idea of the significance of this. And I will call this form 2 really the primary form of the law of sines. Now, there are various ways that this can be stated in plain English. One way that it can be stated in plain English, probably the best way, is that in a triangle, sides are proportional to the sines of their opposite angles. Okay? Alpha is opposite A, beta is opposite B. So what we've said is that the sides are proportional to the sines of their opposite angles, which just means that you want to get the ratio of a pair of sides, form the ratio of the sines of their opposite angles. Yes.
Is that what you did with the slider thing at the bottom of the page, where it was GeoGebra?
Probably. That's probably the formula that's in the background that makes that happen. Okay. Now, I do want to reflect on this for just a moment because sometimes I think that students don't really get the significance of this. So let me talk for a moment about an assumption that I've had many students make in the past and say to me more or less explicitly and think that it was just obviously true or ask whether it was true. It's this. In a triangle, they would say, sides are proportional to their opposite angles. That is something like this. If I had a triangle and one angle was double another angle, then the side opposite the double angle would also be double the length. That ain't true, okay? And you can provide counterexamples to that fairly easily. So let me show you a really easy counterexample to that. And then I will say what is actually true. What is actually true is the law of sines. So you remember the 30, 60, 90, right? You better for the test. So if the small leg is 1, what's the hypotenuse? Hypotenuse is just 2, and the longer leg is square root of 3. That's exactly right. So what about this conjecture that students made, or this outright assertion that sides are proportional to their opposite angles? Well, if that were the case, then the ratio of 30 to 60 would have to be equal to the ratio of 1 to root 3. I have just said that these two angles are proportional to their opposite sides. Well, is that true?
No.
That's not true, okay? That is surely false. So in general, it's just false if you like double an angle, you double the opposite side. That's just not true. What is true? Well, what is true is that the sides are proportional to the sines of their opposite angles. So if instead of simply 30 and 60, I were to write the sine of 30 and the sine of 60, that's absolutely true, okay? That's absolutely true. And that's really cool and powerful, okay? As for like sort of useful real world mathematics, sort of like what engineers would actually use, this, without a doubt, of anything that's been said so far in the class, this is the most useful formula that we have encountered. There'll be another one as well called the law of cosines, but this is genuinely useful. And let me show you what you can do with this, okay? Let's create, again, I'll just make an acute triangle. Okay, so again, the situation in section 8.7 is I know the angles and a side. and I want to find another side. That formula allows me to do that very, very quickly. Yeah.
Can I try to predict what form to the law of cosines is?
Not yet. Did you imagine that it looks a bit like the Pythagorean theorem but modified?
I was thinking it looked like the law of science, but modified.
It's more complex.
Oh.
It looks like the Pythagorean theorem but modified. What the law of cosines looks like is, or actually what it is what the Pythagorean theorem has to become when you correct for the fact that you no longer have a right triangle. It's like the Pythagorean theorem and then a correction factor because it's not a right triangle. Anyway, so let's build an acute triangle. So somebody give me an angle measure.
30.
30 degrees. Somebody give me another one so that the triangle will be acute.
21.
It won't be acute.
Yeah.
74 degrees. I think that'll work on it. So that's 104 degrees, and the final angle has to be what? 76 degrees. So there we go. There's an acute triangle. Okay.
Definitely.
And let's say that we know a side length. So somebody pick a side length.
12.
12. Which side is that?
The opposite of 30.
Opposite 30. Okay, so that's the 12. And let's say we wish to find a side. So either the side opposite 76 or the side opposite 74. Okay, so we'll put an X right there. Okay. Now, here's what the law of sines can do for you. The law of sines says that sides are proportional to the sines of their opposite angles. So here's what we can do. I can say that x over 12 must equal the sine of 74 over the sine of, yes, the 74 is opposite the x, the 30 is opposite the 12, and this is what the law of sines says, okay? It says that sides are opposite to the sines of their opposite angles. And then you can solve this out, okay? You can solve it out. It's not difficult to do. Cross multiply, get the table, use your calculator, whatever. And then here's something else you can do. So let's build one more acute triangle, okay? And again, it doesn't matter. It doesn't have to be acute, but I do need examples. It would work if it was right or obtuse. So let's build another acute triangle. Give me an angle measure.
69.
No. And I can't believe you have the temerity to actually spit that out like that. So we might have a conversation later. Somebody give me an angle measure. 40. And another angle measure. Yes. 45. Will it be, it won't be acute, will it?
Yeah, well,
How about 55?
55. Yeah.
And then the final angle measure will have to be what?
85.
85. Okay, so there we go, acute. So I don't even know why I told you to build an acute triangle. It would work if it wasn't acute. So here's what I want to do in this case, okay? I want to get the ratio of a pair of sides. Notice what I didn't say. I didn't say I want to get a side length. I didn't say that because it would be impossible if I haven't given you any. But I can get a ratio of side lengths, and that should not come as a surprise that that's possible. Because what do you know about any two triangles with these angle measures? This tiny one over here and this massive one over there. What do you know about them? Any two triangles with the same angle measures are?
Isosceles on the field.
Last chapter. This triangle here, that triangle there. The angle measures are the same. Those two triangles are similar, which means that sides are. And what is a proportion after all? It's equal ratios, okay? So it doesn't matter what the size of this triangle is. The side ratios, they're set. They're set as soon as I specify the angle measures. They're out there in mathematical reality if I could only find them. Well, let me show you a path to them. It is the law of sines. So let's say that I want to get the ratio of the sides opposite the 45 and the degree angle. That's just straight law of sines, okay? So the ratio of A to B is the ratio of the sines of the opposite angle. So that's the sine of 55 degrees over the sine of 85 degrees. And the sine of 55, that's a number. The sine of 85, that's a number. So you divide those two numbers, and you get the ratio of A to B. Okay? So that's how you do that. The law of sines does that for you. See how much time we've got. And I do want to go ahead and talk about the next section just a little bit. section 8.8. I will definitely come back and talk to you about this next time. But I think it would be good to go ahead and start, and then to say that officially 8.8 is assigned, though honestly I know it will be a bit of a struggle, and we'll need to work on it. Okay, so here's what we'll do in 8.8, and I'll try to make this short and continue the story next time. So in section 8.7 it was, I know the angles in a side, and I want to find another side, and maybe the third side too, okay, but at least one more side. Here I know either two sides in the included angle, SAS, or I know all three sides, okay, and then I want to find an unknown. What we'll do with side angle side, and let's say this is the one that we'll look at today, okay. What we'll do with side angle side is we'll find the unknown side length, okay. We'll find the unknown side length. Now, of course, when we come on Monday and talk about the side case, we know the side length, so of course we'll find an angle measure. I also talked about that with my previous class, but I kind of regretted it was too much. So let's just talk about side angle side a little bit. So what will we do? Well, we'll drop in an altitude, of course, because that's how we generate right triangles. And we need the right triangle so that we can do trig. Now the question is this, okay? When we had, well, back in the previous section, when we knew the angle measures, we knew about the locations of the altitudes, because those depend on the angle measures. Okay? If it's like an acute triangle, all the altitudes are inside. If it's obtuse, the altitude from the obtuse angle is inside, but the other two are outside. Okay, so it depends on angle measure. But in this case, side angle side, we don't know any of the angle measures. Well, we know one. Sorry, we obviously know one, but we don't know the others. Okay, so we don't know necessarily whether the triangle is acute, right, or obtuse. So that means that there's like this issue. It's like, okay, so which altitude do I put in, and how do I know where it is? And doesn't that matter? And it does, okay? And there's a way around the problem. So let me begin to talk to you about how you get around the problem. And basically the advice is what I say here. Where do you put in the altitude? From the vertex opposite the larger side, okay? From the vertex opposite the larger side. So let me just show you an example, okay? So here is the side angle side type case. I've got this triangle RST with a pair of sides 9 and 6 and an included angle of 72 degrees. And I want to find the third side. That is, I want to find the length of RT. I need to drop in an altitude. Three possibilities, right? Because every triangle has three altitudes. First bit of advice, don't drop in the altitude from S, the angle that you know, because you then will have split S up into two parts and you won't know what those parts are. So if you want to do trig with an angle, you've already got a hurdle in your way because you don't know any acute angles of any right triangle, so don't do that. So the question now is this. Will I take the altitude to the 9 or will I take it to the 6? My advice, take it to the 9 because we know where that altitude has to be. Okay. Here's the logic of it. So that triangle that you see in front of you, it's either acute, right, or obtuse. Okay. If it's acute, what do you know about the altitudes? They're all on the inside. So if I do the altitude from R, it's on the inside because they all are. If it's a right triangle, what do I know about angle R? That's the right angle. Because angle R is opposite the 9 and angle T is opposite the 6. So angle R has to be greater than angle T. And I already know that angle S is 72 degrees. So if this is a right triangle, I don't think it is, but if it were, angle R would be the right angle. And the altitude from the right angle is on the inside. And it works very much in the same way for obtuse. So let's say that this turned out to be an obtuse triangle. I don't think it is, but it might have been. Angle R would have to be the obtuse angle. How do I know? Well, S ain't it. That means that either angle R or angle T is the obtuse angle, but it will have to be the larger of the two angles, which means it will have to be opposite the larger of the two sides, which means it would have to be opposite the 9. So no matter what kind of triangle this is, the altitude from R will have to be on the inside. And you can always repeat that logic, okay? So take the altitude to the larger of the two given sides, and you know it will be on the inside, okay? And now let's actually talk just a little bit about how you would do this problem, okay? And then I'll hush up, okay? So I dropped in the altitude to the larger of the two given sides. And again, what I want to get is RT, okay? That's what I want to get, which I'll call just maybe X, okay? So that's my final goal. Well, here's something that's happened. That side of 9 got split into two parts that I'll call one of them Y, and then the other one has to be 9 minus Y, okay? Oh, and then I do know, of course, tell you what, I'll call the altitude, foot of the altitude F. I do know the final angle in triangle SRF. It's a right triangle with a 72-degree angle, so that has to be 18 degrees, right? Yeah, I think that has to be 18 degrees. Now let's write down some equations, okay? And it will take more than one. And it might well be the case, indeed it almost always is the case with these, that along the way I'll make use of the variable h, okay? So let's see, what are some things that I know? Well, here's something that I know. H squared plus y squared is equal to 6 squared. That's what? Pythagorean theorem, because triangle SFR is a right triangle. Okay, so let me also continue to think a little bit more about triangle SFR. Ooh, I've got side lengths and angle measures, so I can do trig with it, right? Ooh, I can do like this. I can do the cosine of 72 degrees is, by definition, adjacent over hypotenuse. In triangle SRF, the adjacent to 72 is the what? It's the y, and the hypotenuse is the 6. And it's like, oh, now I can do something, right? So let me solve this equation for y, and I get y is 6 times the cosine of 72 degrees. That looks a bit better. So 6 times the cosine of 72 degrees, and then I can substitute that back in to the first equation now, can't I? So I can go h squared plus, instead of y, 6 times the cosine, I don't know why I keep on doing that, the cosine of 72 degrees squared is equal to 6 squared. And I can solve that for h. Okay, I'm not going to take the time to do it, but it's not hard at this point. H is the only variable that remains, so I can solve for h. And then once I get h, well, I can also go and get y, can't I? Look back at that first equation. H squared plus y squared is equal to 6 squared. I'll have h, okay? And so I can plug my value for h in, and then I can get the value for y. And now look at triangle RFT. Once I've done all the work that I just described, I'll have the value of h, I'll have the value of y, which means I then know the lengths of both legs, which means I can get the length of the hypotenuse, which is the x that I want. Yes, sir.
All right. I was following right up until you started getting the length of y.
Okay, so you agree that I can take the equation that I reached at the bottom and get h, right?
Same thing. Okay.
Yeah, and so, I mean, basic algebra, get h, and then once I've got the h, I can plug it into that first equation, get y. Yeah.
Why didn't you just solve for y and then solve for h?
The other way around?
Yeah.
It's going to be the same amount of work either way.
Oh, okay.
I could do like sine perhaps, and do like the sine of 72 is h
No,
over
like-
6. No,
Like
go ahead.
6 cosine 72, why don't you just like solve that out to get y? And then use Pythagorean theorem to get h.
It's the same thing. I just didn't like plug it into a calculator. So, yeah. My tendency is to wait until the very end to plug anything into a calculator. Yeah.
What's the symbol of the next to X?
What's the what?
The symbol next to X. What's that?
It's
Oh, just
an
me
arrow.
pointing. Sorry. Yeah, nothing special. It's just an arrow. Yeah.
Question, I don't know how we got cosine 72. I can't remember how we got cosine 72 equals y over x. Was that, I thought we were doing the
Y over 6.
y over 6. I thought we were doing that proportions over proportion, proportions of sine over proportions of sine.
Section 8-7.
Okay.
For the, I know all the angles in one side. This is new kind of problem, where I knew two sides in the included angle. And the reason I wrote that, that's just the basic definition of the cosine function.